Hello all, welcome to the second session of interference. Today we'll be discussing Young's double slit experiment. So before going into the details, let us look into the history of this experiment. In 1801, an English physicist called Thomas Young established the concept of wave nature of light through his Young's double slit experiment. And in this experiment, he made a pinhole camera in cardboard and allowed sunlight to pass through it. This white light was then allowed to fall upon another cardboard having two pinholes placed together symmetrically, and the emerging light was received on a plain screen placed at some distance. At a given point on the screen, the waves emerging from two holes had different phases, interfering to give a pattern of bright and dark areas. Such a variation of intensity on the plain screen demonstrated the light waves emerging from two pinholes, and the pattern of bright and dark areas can be sharply defined only when the light is of a single wavelength or if the light source of light is of monochromatic light. So going on to the experimental setup. Here, this picture shows the experimental setup of Young's double slit experiment. Here, A and B are two parallel slits separated by a small distance d, which is then illuminated by a monochromatic source of light waves of wavelength lambda. And this A and B are perpendicular to the plane of the diagram. And these A and B, these two parallel slits, acts as coherent sources. And here S is the screen placed at a distance capital D from A and B. So let's find out the expression for these alternate dark and bright fringes. For this, we are considering small d as a distance between these two coherent sources A and B. Aയും Bയും തമ്മിലുള്ള distance ആണ് small d, and this is illuminated by a light of wavelength lambda. And we have placed a screen XY at a distance capital D from A and B. And we have marked a point on the screen capital O which is equidistant from A and B. And C is taken as the midpoint of A and B, and P is any point at a distance x small x from O. So ഇതാണ് നമ്മുടെ experimental setup. That is, we have two slits. അവ തമ്മിൽ തുല്യ ദൂരമാണുള്ളത്, equidistant ആണ്, and the light coming from through these slits are allowed to fall on the screen which is placed at some distance, ഒരു fixed distance capital D ഒരു സ്ക്രീൻ പ്ലേസ് ചെയ്യുന്നു. ആൻഡ് ഇൻ ദ സ്ക്രീൻ വി ക്യാൻ സീ ദ പാറ്റേൺ ലൈക്ക് ദിസ്. സെൻട്രൽ ഓയിൽ വിൽ ഗെറ്റ് എ ബ്രൈറ്റ് ഫ്രിഞ്ച് ആൻഡ് ഓൾട്ടർനേറ്റ് ഡാർക്ക് ആൻഡ് ബ്രൈറ്റ് ഫ്രിഞ്ചസ് ആണ് നമ്മൾ ഒബ്സർവ് ചെയ്തത്. സോ വി നോ ദാറ്റ് ഇൻ ദിസ് പിക്ചർ waves traveling from A and B are traveling unequal distance in reaching P. So these at the point P, the waves coming from A and B can be in phase or out of phase depending upon the path difference between these two waves. So we have taken this path difference as delta, and the path difference will be light traveling from B minus light traveling from A to P. So BP minus AP. And in this figure we can see what is BP. BP is BM plus MP. So minus AP. And also it is very clear that AP, this distance AP is same as MP. So we can say delta is BM. And now we have to find out an expression for BM. And in this right angle triangle ABM, you can see what BM is D sin theta. And if theta is very small, sin theta can be approximated to theta, hence BM will be theta. So the path difference will be theta into D. And again you see another right angle triangle COP, this triangle COP. Here you can see tan theta is OP divided by CO. That is OP is distance x divided by capital D. So again, for small values of theta, the tan theta can be approximated to theta. So theta will be x by d. And we are substituting this expression in the equation of path difference delta, that is theta into d, will become x into small d divided by capital D. So this is the path difference. Now we know that by the principle of interference, condition for constructive interference will be the path difference is equal to n lambda. So we have x into small d by capital D is n lambda, where n is 0, 1, 2, 3, etc. indicates the order of bright fringes, and x is equal to, from this expression, x is equal to d capital D by small d into n lambda. So this gives the equation for the distance of the nth bright fringe from the point O. Again, for the dark fringes, we know that the condition for destructive interference, this will be 2n minus 1 lambda by 2, where n is equal to 1, 2, 3, etc. And we are substituting in the equation for path difference, x into small d by capital D is 2n minus 1 lambda by 2, which gives the equation for the distance of the nth dark fringe from the point O as capital D by small d into 2n minus 1 lambda by 2. So we can say that on the screen we can see alternate dark and bright fringes on either side of the central bright band. So this is the interference pattern we are getting on the screen. At the center we will be having alternate, this is the center bright branch, and on both sides of the center fringes, the central bright fringe, we can see alternate dark and bright fringes. So the interference pattern will be like this way. And we have to find the bandwidth also, how these bands are separated. So the distance between any consecutive bright or dark band is called the bandwidth. So we can see the distance between n plus 1 and nth order consecutive bright fringe will be xn plus 1 minus xn, as this will be giving capital D by small d into lambda. And similarly, if we are taking consecutive dark fringes, we will also get the same expression. Dark fringe ആണെങ്കിലും bright fringe ആണെങ്കിലും bandwidth in the expression will be the same, that is capital D by small d into lambda. From this expression we can see that the bandwidth or fringe width is directly proportional to d, the distance between the screen and the source, and it is directly proportional to the wavelength lambda of the light used, and it is inversely proportional to the distance small d between the sources. So for a given wavelength of light, beta or the bandwidth can be increased either by decreasing small d or small d യുടെ വാല്യൂ കുറയ്ക്കുകയാണെങ്കിൽ we can increase the bandwidth. Small d എന്ന് പറഞ്ഞാൽ it is the distance between two slits. Or നമ്മൾ സ്ക്രീനിൻ്റെ ദൂരം കൂട്ടുകയാണെങ്കിലും bandwidth will be, if d is increased too much, the bandwidth will be very low, or the intensity of the bright band diminishes if we are keeping the screen at a far distance. So thank you. That's all for today.